Hi up and welcome back to Geol James with me, Jim Gelder. Tell you what, I am absolutely buzzing at the moment. Not only did I get to present to the early career professionals of the BGA and Engineering Group of the Geol Soc last night, but I've also had a much bigger response to the YouTube channel than I was expecting or possibly hoping for. So over 3,000 people saw the post I put up on LinkedIn referencing it, and over 200 people watched the introduction video as well. So if you're one of them, sincere thanks, very grateful. If you're one of the 20 people that subscribed, very grateful to you. If you haven't subscribed, please consider just taking the half second it takes to hit the subscribe button. It's great for me, and it'll help more people get connected to me gobbing off about engineering geology. So look, that's it. Loving it. It's going better than I hoped. First proper video follows after this. It's the talk I gave yesterday on buried obstructions and utilities in the ground. Something that I'm really passionate about. I think we ought to be able to do much more, much earlier in project conception, using desk study, existing records, literature searches, and surveys in the field, to be able to hopefully find a way to design out the risk of having to uncover big things in the ground or dangerous things in the ground when we get to construction. So no more messing about. I'll get out of the way, and please enjoy the talk from last night. Able to talk on any occasion, but especially to early career professionals. I'm going to be talking this evening about buried obstructions in the ground and also utilities, and how those risks and hazards manifest themselves, and how best to manage them. I personally feel from my experience that it's an area that in general we could probably do better at across the industry, and hopefully by the time I finish this evening you'll understand why I think that. I'm going to Gary's already mentioned the mentee. It's really two questions. I would like you to think about the hazards associated with buried obstructions in the ground and the hazards associated with buried utilities. And there's one question around hazards and another question around mitigations. I'm going to give a bit of context. I'm going to go through 3 case histories that will hopefully inspire and trigger thoughts in your brain around hazards and mitigations. But I don't believe I've got an exhaustive list, so I'm relying on a tremendous amount of insight from everybody on the call. So please, if you have got access to a browser on the side, go to mentee.com, enter that code and stick as many hazards as you can in the hazards question and as many mitigations as you can in the mitigation section, and we'll have a look at those a bit later on. The 2 pictures are from the case histories that I'll be talking about. The one on the left is very congested infrastructure, new and old, in the ground. The one on the right, a site investigation with very congested utilities. Yeah, so that's it. Good luck with the mentee. Just before the Second Gulf War, there was an awful lot of focus on intelligence, and Donald Rumsfeld, Secretary of State for Defense, was briefing the US government on the state of that intelligence, and he introduced this terminology around known knowns, things that we know. So in the context of tonight's talk, that might be a foundation in the ground from a building that's been demolished, for which we've got a really good
as-built drawing, and we can see the outline of the footprint on the ground. So that would be a buried obstruction. We know it's there, and so that's known knowns. But we also have known unknowns. Very often, service drawings are schematic. So we might know that there's a gas pipeline following a road, but we don't know where in the road it is. And they become our known unknowns. And then there's also unknowable unknowns, things that you just can't know are buried in the ground until you encounter them. One good example of that was a site investigation we did at the Port of Boston, where a borehole struck an electricity cable 6 meters below ground level. It wasn't on any drawings. It wasn't known to the operations team. It wasn't in any sensible sort of location for anything that you could have imagined, but there it was. And that's really residual risk, but it's also potentially very high risk. So those are the sort of three boxes, and hopefully you'll see that terminology unfold throughout the talk. The pink box is a box I'm quite passionate about, insofar as things that are knowable but unknown. The more effort you can put into moving things from that pink box to the yellow one by investigation, by really tenacious literature search and searching for records, the better for everybody. The earlier you can develop as complete a picture as possible of what might be buried in the ground, whether it's demolished buildings, services, or whatever, the better for the project. And that's a real passion of mine. So a quick look at what the Eurocode says. As with most things in the Eurocode, it says everything and nothing. Doesn't refer to buried obstructions or services specifically, but in planning the design investigation, it says that we should provide enough information for adequate design of the temporary works. And so if you've got to manage during construction with buried obstructions, buried foundations or whatever, then that fairly squarely falls into that category. We've got to provide the information required to plan the method of construction. Same story. And we've got to be able to identify any difficulties that may arise during construction. All three of those squarely pointing towards our duty of care to have properly investigated and defined, as far as reasonably possible, things that are buried in the ground that aren't readily identifiable, known unknowns and unknowable unknowns. Design investigation shall identify in a reliable way the disposition and properties of all ground relevant to or affected by the proposed construction. Imagine working in a water treatment works where there's a buried tank in the ground, an old partially demolished tank, and part of your new structure is going to be on it, part of it isn't. You really need to know as early as possible where it is so that you can design around it. Presence of waste and man-made materials. Well, all buried obstructions and utilities are man-made materials, and the history of the site and its surroundings shall be taken into account. That's all good, but that's the design investigation, which comes in the Eurocode after the preliminary investigation. So which comes first, the chicken or the egg? Do you design your layout and then manage the risks that are in the ground, or do you investigate the risks that are in the ground and then design your layout? And there isn't a one-size-fits-all answer to that question. It's always complex, but hopefully you'll get some clarity on some approaches that we can take. So I think it's really important that for any site, as early as possible, you consider the complexity and the amount of experience or precedent that you've got for any aspect of the project. And specifically for what we're talking about, that's the complexity and precedent of the engineering that we're undertaking, the complexity and amount of precedent of working in a specific geology, And then for buried obstructions, the complexity and experience precedent of working in the Anthropocene, that is man-made problems. So the 3 case histories, 2 from Boston, 1 on the left bank of the quay, and I'll show you that in a second, 1 on the control room and 1 from a GIO water treatment works. For the left bank, our geology is relatively benign, our natural geology. And for a sheet pile wall, there's it's glacial till, for which there's plenty of experience and precedent as well. So down here, our geology is relatively benign. But we're interacting with a new quay wall with an existing quay wall. That means the engineering is very complex. And when I go through the site history, you'll see that the Anthropocene is also very complex in this red box. And really, we need to be doing as much as we can as early as possible in the project to allow the design concepts to fit around the dragons and monsters that may well be in the ground. The control room, the geology and the Anthropocene issues are much the same level, but this is a G+1 building on a raft foundation. The engineering is much more simple. For the ground investigation, actually the geology here is much more complex. The engineering is really quite complex. Excavations for tanks below ground level that themselves need piling, and piled foundations for structures through ground that may contain historic foundations and buried artifacts. The Anthropocene also in a similar place to Boston, very complex because there's so much buried in the ground and relatively little available records of what's there. So we've done our best, but there may still be problems in the ground. And this kind of classification I find really helpful to have discussions with peers, our design teams, contractors and early contractor involvement, and discussions with clients to make sure that everybody's in the right space for how nasty it might get when you start digging holes when there's stuff that we don't really want to be there. So back to the Eurocode. The definitions of the 3 geotechnical categories are okay, helpful, but not exhaustive. They don't really deal with buried obstructions in any explicit way. And so those matrices that I've just presented, I think are really helpful. You're never going to be in geotechnical category 1 if you've got congested utilities or buried obstructions. You will probably be in geotechnical category 2, but in certain circumstances, you may involve abnormal risks, exceptionally or unusual difficult ground conditions, probable instability. So there are instances where I think buried obstructions could carry you into category 3, but the majority of the time you'll be in category 2. Okay, so on to the case histories. Case histories 1 and 2, Boston. There's Boston in Lincolnshire on the Wash. A GA of the project. It's a flood defence scheme. So there's flood walls, new flood walls, sheet pile flood walls along the right bank of the river. A new barrier structure, enormous structure, 365-ton steel gate operated by 2 55-ton hydraulic rams. And then a new flood wall along the left bank, all of which is in the estate of the Port of Boston, which is well over 100 years old and has a checkered history in its development. Another set of gates and a new entrance into the port, and flood waters seal into an existing flood defence at Lord Foster Sluice. Geology, well, I mentioned it's relatively benign in the natural. We've got glacial till and alluvium in yellow and green. The grey is made ground, which is typically 5 to 10 meters thick, very, very heterogeneous, locally contaminated, and as you'll see in a second, stacks of stuff from the historical development of the port. In terms of site history, hand-drawn map from 1817, and the port is will be in this area, but in 1817 there were just 3 windmills there. By 1889, the port had been constructed. There's the dock and the dock entrance, but there isn't actually a quay wall along the left bank at this stage. It's just the river bank. There's some bathing stations and the Baths Reservoir along here, and a number of buildings around the dock and the dock railway, so some railheads in the dock. By 1905, most of those buildings have been either developed further or demolished and replaced. There's a new ship slipway coming down, and those are the main developments by 1905. Aerial photographs from 1930. Here you can see the slipway, and there's a slipway from the other side, and the dock and the railway. So our new wall is in this area here along the riverbank. By 1952, the left bank has been formalised with a concrete sheet pile quay wall, and this big sugar and grain silo has been constructed at that end. Things getting really quite complicated. By 1966, some more new buildings and railway along the new quay wall, and crane rails in along the new quay wall as well. So from the engineering department at the Port of Boston, we've got this standard detail, which shows a concrete anchorage with anchor ties to a waning on the quay wall at the maximum bending moment, with bollard ties for the bollards that are intermittent along the top of the wall, but also passing reference to this alternative piled anchorage system, which is shown in dashed, with the anchor ties coming and tying onto this piled anchor trestle table. What you haven't got is a dimension, so you don't know where this anchor beam sits, and you don't know where this piled trestle table sits. So here's a potted composite history of all those historical maps, and we are building a new sheet pile wall in this area along here that will need an anchorage system somewhere back here. And actually not long after the start of the design and construct, this black area here was found on a new drawing that was unearthed. That is the anchor beam there and there from this standard detail, and these blue patches here are the trestle table anchorage of the existing quay wall. This was a real problem because the flood wall was proposed to be a sheet pile wall pretty much along this line, and obviously it's not possible to do a sheet pile wall through a big concrete anchor block, and so we had to come up with a different plan. So what I'm going to do now is dip into the Bim model of the job. Here's the river, right bank, left bank. Here's the barrier. This is the area that we're going to be looking at just in here, so that you can see how some of this congestion manifests itself. If I now drop this down so that you can see into the ground, you can see there's the anchor beam for the existing quay wall, and here's the existing quay wall. And if I zoom in a bit, there you can see the anchor ties and the bollard ties as well. We actually did a small trial excavation and unearthed this anchor beam in exactly the position that the drawings suggested it would be. This is a tunnel, a culvert from that grain silo to a crossing that used to take grain to the other side of the river. The Yeah, and the original plan would be a sheet pile wall in this area to use as the anchorage for the new keep wall, which is here at the front. The changes and the discovery of the drawing that helped us lay all this out meant that we had to change our idea for the anchorage, and instead we went for discrete tube pile deadman anchors. This had 4 or 5 specific advantages. First one, we were able to put the tubes either side of this culvert. We were able to put the tubes to the rear side of the anchor beam. We had a degree of X and Y flexibility in the position of the piles, which you wouldn't have if you had a continuous sheet pile wall. So if at any location a pile just wouldn't go into the ground, we could just step it back a meter and try again. That in turn meant that actually we could pre-probe every pile position and drive the piles, knowing that we could get them in. We actually, the contractor drove a pair of sheet piles with a vibro hammer to prove clear driving at each one of these locations before the steel tubes went in. We could also then use the steel tube as a temporary shoring to allow man entry to connect the anchors into the tube. We could connect at a high level so our anchors didn't clash with the anchor beam. Lots and lots of advantages that meant that the risk of clashing with these existing entities was able to be designed out. And then if we just go a little bit further along, here you can see the piled trestle table. Oh, excuse me. There's the piled trestle table, and again with the tube piles, we were able to design around that in plan and have the flexibility that we needed with respect to that. Okay. While I'm in the model, I'm going to skip on to the next case history, which is for the control building, which is highlighted in blue there. And what we'll do is we'll come in from, excuse me, we'll come in from the other side to start with. So there's the control room. I'll just cut it out. There we go. So the control room houses the critical infrastructure required for raising the barrier, the power supply, the hydraulic pumps. Oh, sorry, I didn't mean to do that. Okay, sorry about that. All the critical plant is inside there. Here's the flood wall. So the control room is actually on the defended side of the flood wall, but nonetheless there are individual pedestrian gates and things within the flood wall. There's still a possibility that water may get to the wrong side of the flood wall and potentially flood the control room. And for that reason, within the works information, we were required to make the flood room waterproof. That meant bulkhead doors at ground level to be waterproof, which was small and narrow, which really constrained the M&E plant that we could get inside and how easy that plant would be to service. We needed a standby generator, which would have needed to be on the other side of those bulkhead doors, which was a real problem, which needed exhausting and refueling from above the flood defence, also a big problem. So the solution was relatively straightforward. You move all the critical infrastructure. Also, the other thing was in the flood condition, the building would become buoyant, so you needed hold down piles to stop it floating away. The solution, relatively straightforward. You put the critical infrastructure upstairs, all those problems go away. These are the MCC kiosks for the electrical. Here's the hydraulic oil supply, and the hydraulic pumps are in here. Here's the generator, which is now easy to refuel, an exhaust outside on a platform. And all those design changes inside the building meant that we were able to consider the possibility of not using piles. So hopefully you got that orientation of where the control building is. Here's a plan showing the buried obstructions. In blue, the anchor beam. In pink at the front, old railway tracks and crane rails. Two historic silos here, a raft foundation from a previous building, something infilled associated with the historic baths coming partially underneath the building footprint, and also on here, but more difficult to see, are the buried utilities as well. So we took the opportunity to do a settlement load test. So we cast a small raft foundation, built up Kentledge using legato blocks and sand on 3 levels, installed a bunch of monitoring in there, and we were able to demonstrate through that monitoring that in fact we could use a raft foundation. That although there was a reasonable thickness of made ground, it was predominantly granular, and settlements would be immediate with no long-term risks of consolidation or creep. A view underneath of what it would like. Horror, 70 steel tube piles, clashes all over the place with anchor beams, anchor ties, existing utilities. Significant health and safety risks reduced associated with piling through those buried obstructions, associated with diverting buried services, and excavations required to exhume and potentially contaminated excavations to exhume bits of buried infrastructure. All the clashes designed out and the unknown buried risk reduced significantly in terms of sort of finance. There's obviously the capex saving from the piles and the piling, but also the risk of delay, critical delay. The control room, not surprisingly, is on the critical path for commissioning the barrier. On to the third case study. This is a wastewater treatment works. It's just a ground investigation. Just a ground investigation. Who knows? It's still quite easy to kill someone in a site investigation. We were doing boreholes. We'd done a services search and it got services drawings. We'd laid the boreholes out around those services to avoid them. We'd had consultation with the ops team for anything that they knew from local knowledge. We'd done PAS 182 GPR clearance of the site. We'd done a surface CAT scan. We'd done a hand dug inspection pit, and we'd CAT scanned the bottom of the inspection pit. What could possibly go wrong? The problem was that this was a change. This was borehole 1A. Yeah, I don't know whether it was borehole 1A, but we'd had to terminate a previous borehole, and we'd changed positions and we'd offset. There was perhaps elements of groupthink, that this was about the 10th A, B or C borehole that we'd done where we'd have to offset. We went through a degree of process blindness. We'd gone through all the checks that I've just said and not detected anything. The problem was that there was a polyethylene pipe carrying raw sewage sludge from this wheel here to these pipes over there. And the thing that saved us was the experience, expertise and competence of the driller, who immediately recognised the behaviour of his drilling rods was wrong, stopped work immediately, and that's why we had a near miss and not a very messy and smelly accident. Root cause? Well, we didn't, because it was a change. we moved on through the process without actually just pausing for that amount of time to take a step back and actually look and see these pipes the same colour crossing the area where we were. The big problem was that the pipes were polyethylene, so none of the techniques that we'd used detected them. So that's a case history, a difficult and troublesome case history, where it felt like we'd done everything right, but what we hadn't done is just paused for breath, taken a step back, taken a good look round before we'd reposition the borehole. So here's a challenge. If we struggled to sink a borehole there, how's anyone going to build a piled foundation there? If you think those models that I just showed you at Boston were complex in the ground, it's going to be absolutely horrific for anyone that's got to build a new building in that area, and how you fairly and squarely share the risk between the client and the supplier for that risk is really challenging. And that leads me to this statement that came from a very wise, but I will remain anonymous friend of mine. He says, the tender is an exercise in selecting the most ignorant, most desperate, or most commercially savvy supplier. And none of those things are good for a client, and none of those things, well, certainly ignorant or desperate, are not good for health and safety. And so really a baseline of what is or might be, might be known unknowns, or it might be good imagination of unknowable unknowns, what might be in the ground, built upon a complete a picture as possible, as early as possible in the project is the best way to design out hazards, and designing them out is the best way to reduce risk. You do that early and you apportion risk equitably so that everybody is working in the right environment, atmosphere, space to manage the ground risk appropriately. So mitigations, avoidance. I've given you some case histories now to hopefully help you understand the importance of concept design. Not saying, oh, it's just concept design. If it's concept design, that's when you've got the most opportunity to design out through avoidance of ground risk and utility risk. Of course, you need procedures, risk assessment and method statements, toolbox talks. Brief back is really helpful. So when you give a toolbox talks, you ask the operatives to brief back to you what you've said. A permit to dig system that's signed off before anyone digs in the ground. And if things change, then you stop and replan. Competence is important. You need experienced people with expertise and accreditations, CPCS cards and the like. But behaviours is probably the most important part of competence. So it's no good having poor quality RAMs and half-hearted toolbox talks and permits to dig signed off as part of a grudging approach to paperwork. Behaviours come from the top on site, but particularly from professionals on site, really have to set the bar high in the behaviours that we display so that others will follow those behaviours. That means really high quality RAMs. It means enthusiastic and committed toolbox talks. And it means really reinforcing this stop and replan rather than plough on because we've got to meet a deadline. Detection, yep, technology. I've mentioned most of these already. PAS 182, GPR clearance, cable avoidance tools, scans. You can actually get cable avoidance tool devices mounted on the arms of excavators these days, and you can consider some geophysics as well, specifically to locate buried obstructions. But all of these are very dependent on operator competence, which and also generally have a degree of uncertainty still left in them. I mentioned at Boston we did probing, and that was very successful, and also we dug down and exhumed the anchor block, and those are opportunities that are available to you, but exhumation in particular, as soon as you start excavating in this ground, even trial pits where you've got congested utilities, gets really challenging. So my conclusions: get the concept right, understand complexity, and the amount of experience and precedent that's available for a site that's got buried obstructions or congested utilities. Know your known unknowns and investigate them in as much detail as you can. So this would have meant finding the anchor block at Boston a lot earlier than we actually did, for example. Do that as thoroughly and as early as possible. Literature search, record search. You need real tenacity in a desk study in this type of environment. Never accepting, oh, these are all the records we've got because we've lost them. You know, go to the public records office in Kew if you have to. Really challenge again on as-built drawings and available drawings. Go to the Geol library or the ICE library, get literature searches done by librarians. It's amazing what you can find in published papers. Detection by technology, probing and exhumation. Really important. Know how you'll build the works, including how you'll manage unknowable unknowns. And if possible, do that at the concept stage. Get contractors involved early, so that part of the Eurocode, you provide the information to build the work safely, is covered off, and you can plan your investigations around that. Or you can say, well, we'll mitigate it at the construction stage, but understand what that means in terms of risk for buildability and design. Avoid this risk as far as you can through design, and if you can't, develop a baseline so that the risk can be shared equitably when you get into design and construct tender. I'm very nearly done. Here's an example of what this might look like. Here's a model of an old demolished service reservoir with columns that used to support the roof and a base slab and walls and excavations for pipe work and what have you. This green slab is a proposed new foundation that goes in next to it, and you can see there at a glance all the clashes that are going to be encountered and what needs to be considered in terms of dealing with these buried obstructions before we put the new foundation in. That's what I mean by investigating early, thinking through the buildability and sharing risk equitably. Back to the conclusions: procedures and competence. One's no good without the other, and really competence is important, but it's those behaviours, those attitudes, and that tone that comes from the professionals on site. So lead by example and challenge. And when you get change, stop, pause for breath. Don't horse on. Replan, but replan with clarity. Make sure you take a step back, zoom out, and reassess what might be there, not just what is thrown up through your process. So that's around about it. I like to put in a cheeky pitch. I've just set up a new YouTube channel. It's called Geol James. And this talk will be on there fairly soon, and I'll be getting up. This is one of my hobby horses, buried obstructions, but I've got dozens of hobby horses, and I'll be putting up similar sort of videos around a range of topics relating to engineering, geology, and ground engineering. So please, if you find the time, check that out on YouTube. Give us a subscribe and a like. I'd be greatly appreciated to help me get a bit of momentum behind the channel.